Cool, huh? The printer melts the plastic and deposits it layer by layer. As the bottom layer cools and sets, another layer is deposited on top, making it possible to print a 3D object. But it's plastic. What if it were living cells? Can you imagine the possibilities? Ending animal testing, ending transplantless and organ rejection, and all we have to do is substitute the plastic for cells, right? Well, not quite. Let me take you through the process of 3D bioprinting. First things first, the cells. Try to imagine them as these marbles. If you try to pile them up on their own, they'll fall apart. So how do the cells in our body stay together? They have something called an extracellular matrix. It acts just like glue and keeps the cells connected. It also provides communication between cells so they can exchange material and information. But the extracellular matrix is also composed of complex protein structures that cannot be printed. So how do we get around that problem? The answer is bioink. The cells are mixed with a viscous bioink, which is made of a gel-like material that provides a medium where the cells can sit on while keeping their 3D structure, as well as nutrients for them to grow and proliferate. This mixture is then loaded onto the nozzle of a printer. Now the cells have to leave the nozzle. The cells are printed as a thin filament composed of cells and bioink mixture, just like the plastic in a conventional 3D printer. The mixture, however, needs to be in liquid form when it's printed, and viscous after it's printed. For this, the nozzle either slightly heats the mixture, being very careful to preserve the cells as too much heat can damage them, or it uses shear thinning, which increases motion of particles by increasing pressure in the reservoir, always being careful to preserve cell health as too much pressure can damage them. Some structures do not have a flat area, such as the 3D printed heart shown in the beginning of the video. If you can recall, our printer printed some plastic supports in order to print the suspended parts. As we cannot print these supports out of living cells, there are some structures that have to be printed suspended in a water-soluble gel that can later be dissolved. After the structure is fully printed, it is placed in an incubator where the cells can grow and proliferate and create an extracellular matrix in order to create a living tissue. Very simple, right? So why isn't it being used yet? Well, 3D bioprinting is still under a lot of study, and there are still many big question marks we have to consider before releasing it to the public. For example, there are many different methods of 3D bioprinting. We reviewed the extrusion method, which is the most used, but which ones are best for which cells? A fully functioning organ has not yet been made. What are we missing? Will this be accessible to the public? See you guys in the future.